Good evening, everybody. Can you hear me? And can you watch me?
Yes, sir.
Thank you. Yeah. Good evening, everybody. I'm Venkat Subbaradi, as all you know, I think, a research scholar at University of Hyderabad. So I'm here to solve some previous assignment problems here. Let me show you the question paper. So this is the question paper. So let me solve the first problem here. Let me read it. Let A belongs to C n cross n, that is n cross n matrix with complex entries, be a normal matrix, and given a matrix B that is equal to U star AU. Here U star is that transgate of U, that is nothing but conjugate transpose, and it is given U is unitary matrix. Then which of the following is not true? That we have to see. It is asked the false statement. So let me solve the options one by one. So what it is given is, first problem, E belongs to C n cross n. It is given as normal, comma, B equal to U star AU, where U is unitary matrix. Unitary matrix is nothing but satisfy a properties like normal matrix, but of course that has to be equal to identity also. That means U is not unitary matrix, that is U into U star equal to U star into U equal to identity. When a matrix U satisfies this property, we call that matrix as unitary matrix. Nobody? So the first option here it is. B is a normal matrix. So let me first option. So we call the matrix. Let me write the matrix. The definition of normal matrix firstly. People are joining. So we call a matrix. We call the matrix A belongs to C n cross n normal if A into A star equal to A star into A. So here it is given, A is given that it is normal. So we have this property. The first option is B is normal. We have to check with this or not. So it is given that B equal to U star AU. So B star. We have to check this matrix equal to B star into B or not. So let me calculate the value of this matrix firstly. So we get B is nothing but U star AU, that is given, and B star is U star AU whole star. So by the property of transgate, we can write the second matrix as, this is U star AU into, this can be written as U star A star U. Actually it is U star whole star. This is nothing but U. So I am not writing that. So this is equal to U star, by the property of associativity, we can write this is equal to U into U star A star U star. So it is given
Then
that
this is
yes,
U only, not U star.
yes, any doubt?
In the last step, you have to write U star U only, not the U star.
Yes, yes, okay. Yes, thank you. So this is equal to U star A star U. So let me calculate the value of B star B also. From that we can check whether the two matrices are equal or not. B star B, this is equal to, similarly, U star AU whole star into U star AU. This is equal to U star A star U, and this is equal to U star AU. By the property of associativity, similarly, we get U star A star A U, and we have that A is normal matrix. So in the middle term, that A star A can be written as A star, that I'm just replacing with A star. So if you check these two matrices, we can see both are equal. So B into B star equal to B star into B. So B is normal. That is, B is normal. So first option is true, but it is asked to check the false statement. So let me show you the options again. So the first option is not correct. Second option is A star B is a normal matrix. We have to check that. A star B is normal or not. So let me check the same properties here also. That we'll check the matrix A star B into A star B whole star. That is equal to A star B whole star into A star B or not. This is A star B whole star. So we'll check this. This is A star B. This will get B star into A. Similarly, we will check. There is nothing to proceed again with this. Of course, we can write B equal to U star A U star, no, B star. Sorry, what is it is given? B equal to U star AU. We can replace that B with that U star AU, but we will get very difficult calculation. Let me stop with here only and proceed with the another calculation that we have to check with another. That is A star B whole star into A star B. So we will get this equal to B star sorry, in the first it is not correct. Here it is A star B into B star A. Here we will get B star A into A star B. That you can see these two matrices are not equal. So we can say A star B is not normal matrix. So the option B is the correct. Of course, we have to check the options C and D also. I'll explain the options how to check. So here answer is not there, so I'm just marking with red mark. Then you can understand the correct option. So the third option is for all x belongs to C power n, norm of A star x equal to norm of AX. This is a true statement. I'll explain you how to check. So let x belongs to C power n. So we have to check that norm of A star x equal to norm of AX or not. So let me consider the inner product A star x comma A star x. This is nothing but the square of the norm A star A star x. Let me calculate what is the value of this inner product. So from this we can write this is equal to A star x comma x. This is just a property of inner product. I think this is the first property only of the definition of inner product. So we can replace that a star with a star a, because we have that a is normal. So again we can write this is equal to ax comma ax. This is again the same argument that the first property of inner product definition. So from this you can see that norm of a star x comma a star x is equal to norm of ax comma ax. This is nothing but the norm of a star x whole square. This is norm of ax whole square, because we have that ax is the norm is the positive quantity always. So whenever two quantities squares of two quantities, positive quantities, are equal, then we have those two quantities are equal. Because of course if it is not positive quantity we can get plus or minus, but here we have that the norm is always positive, so we can write those two are equal. This is since norm is positive quantity. This is the reason. So the third option is correct. I mean the statement is true. According to the question it is asked, that is not a correct option. So the fourth option is range space of A is orthogonal to null space of A. This we will check. We will check this by taking two elements in two sets. Let me take x belongs to range space. X belongs to range space of A, range space, and y belongs to null space of A. Now we have to prove that, we have to check whether inner product of x comma y equal to 0 or not. If it is 0, then we can say the range space and null space are orthogonal to each other. This is nothing but just the definition of orthogonal property. So we will consider this the left hand side property, inner product of x comma y. Because x is in the range space of A, that means since, let me write clearly, since x belongs to range space of A, we can write x equal to a z for some z in C, the domain of A, range space of A. We can write x equal to a z for some vector z belongs to C power n. I think this can understand everybody. So now we will consider the inner product of x comma y, that is equal to inner product of a z comma y. This is nothing but inner product of z comma a star y. This is a simple property, the first property of the inner product space definition. So I can write this is equal to 0 directly. Can anybody tell me what is the reason for this? We have that y belongs to null space of A, but here I am just writing the inner product of z comma a star y equal to 0. But we have y belongs to null space of A, not a star. Can anybody tell what is the reason? Okay, let me tell. So from the third option, that here you can see a star norm of a star x equal to norm of ax. That means whenever, suppose here instead of x I am just replacing y. So we have that ay equal to 0 because y belongs to null space of A. So we have that this norm of ay equal to 0. From that we can say norm of a star y also equal to 0. So we get that this is nothing but inner product of z comma 0. So that is nothing but 0. This is how it is equal to 0. Does anybody have doubt here? This is just from the third option. From third option, C option. So from this we can say range space and null space are orthogonal for a normal matrix. Is it clear, or anybody have any doubt in this problem?
Sir, I have, sir.
Yes, please.
Sir, you told that if it satisfies A star is equal to A star is equal to A equal to I means we say that A is a normal matrix, sir.
Yes, yes.
If B also satisfies that can B star is equal to B star, B is equal to I also, we can say that B is a normal matrix, sir.
Yes.
Then from the combination, what we have to say, sir?
From that
That
combination,
AB is a normal matrix, like that we can say.
A-
We like that say, sir.
AB is a normal matrix.
Okay.
No,
Okay,
no,
sir.
no, 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 no. I'm not saying. I'm just asking. You are asking that AB is a normal matrix or not?
Yes. Yeah, I'm that both conditions are A and B are normal matrices are here.
Yes,
They are
yes,
satisfying the two conditions.
yes.
Then what we have to say is that from the combination of AB.
Whether AB is normal or not.
Yes, sir.
Yeah, let's
Sir,
check.
it need not have to be normal, no, sir. If A and B are normal, is the product again normal matrix?
Need not be always.
Need not be.
For
I
some
think,
matrix, yes. For
sir, but
some
A star and B star are normal, sir. If A
A,
and B are normal, are
yes.
A star and B star normal or not?
What A star, B star.
A star,
This
that's
one.
one. Sir,
Okay.
A and B are normal matrices.
Yes. Okay.
So is A star a normal matrix?
Yes. A star. You can check that it is Hermitian.
Yeah. If you
Hermi
check, it will satisfy the condition of the normal matrix.
Yes. Actually, this is Hermitian matrix. That means it's a star equal to the again the same matrix. This is equal to A star again.
Hmm.
Do you agree? Suppose let me take M as Hermitian.
Hmm.
That means M equal to M star.
Okay. Hmm.
So from that we can say M star equal to M square and M star M also equal to M square.
Hmm.
So you can see that the here M is normal. That means whenever M is Hermitian, we can say M is normal. So
Hmm.
from that property, you can here say that A star equal to A
Normal
star is
matrix.
normal matrix.
Normal
Yes,
matrix. But A plus B, A into B need not have to be normal matrices.
yes,
Huh?
yes, yes.
Correct.
That you have to check.
Okay. Okay.
Yes,
Hmm. Thank you, sir.
you don't need to check all that property A star equal to B A star A. If you
Hmm.
can check skew symmetric or symmetric, of course, the thing I explained for the matrix M, if it is skew symmetric, then also it is normal matrix.
Okay. Okay.
You
Thank you,
can
sir.
just check the properties. Yeah.
Thank you, sir.
Okay. The second problem here it is A is given again in normal matrix, but of course it is non-zero, that we have to take care of. Then which of the following is true? So the first option here is A power k equal to 0 for some positive integer k. That means they are saying A is nilpotent matrix.
Excuse me, sir.
Yes,
In the previous question,
yes,
I think in the previous question, given
yes,
that A is a normal matrix and B is equal to U star A,
yes,
and combining these two property, I think we can say that B is every normal matrix is diagonalizable,
yes,
and not only diagonalizable, it is unitary diagonalizable. That means
yes,
the the uh, the model matrix is unitary.
yes, this matrix.
So I think she is asking that one. Okay, combining these two property, what can we say about? Uh, uh, I think so. Maybe. So we can say that the U is always a unitary matrix if A is normal matrix.
Yes, yes, we can always say. Actually, here it is. This matrix is nothing but here U star. Of course, here it
Yes,
is defined. The matrix B is here. U is some other matrix, but actually, if we write U equal to U equal to the eigenvectors of A, suppose U is eigenvectors of A, the matrix formed by eigenvectors of A, then we have U star AU. This is equal to the diagonal matrix.
yes,
The this diagonal matrix contains all eigenvalues of A. Of course, here also U is a unitary matrix, but here this U need not be the eigenvectors of A. This can be different, some other different matrix. Okay. So the first option here, it is asked, it is that A power k equals 0. That means A is nilpotent. So that person already told that every normal matrix is diagonalizable. That means we have that A equal to some P inverse dP, where D is diagonal matrix. That means it contains the diagonal entries of D are all the eigenvalues of A. But if you check the option A, they are saying that A power k equal to 0 for some positive integer k. From this you can say all eigenvalues of A are zeros. Do you agree with this? So if suppose if the option A is correct, then we have all eigenvalues of A are zeros. From that we can say D is equal to 0. From that we can say A equal to 0 only. But it is given that A is a non-zero matrix. Let me explain this clearly.
Sir, if all the eigenvalues of A are 0, then we can say that D is 0. That's it.
Yes,
That
yes,
is
yes,
that is fine.
yes.
But how we can say that from that A is equal to 0?
Yeah, and let me explain. So A is given that normal matrix. That means A is normal. That is A star A equal to A star. A star equal to A star A. So we have that, then A is diagonalizable. So we can write A equal to P inverse dP for some diagonal, not for some, actually D is diagonal matrix, having the diagonal entries as the eigenvalues of A. But in the first option it is given that A power k equal to 0. It implies all the eigenvalues are zeros only. Do you agree with this?
Yes, sir.
So from this, can you say D equal to 0? That
Yes.
implies D equal to 0, because D is diagonal. That means all the non-diagonal entries are 0, and the diagonal entries are also zeros here for this option. So from this we can say A equal to P inverse 0 matrix into P. This is nothing but 0, but it is given that A is non-zero matrix in the question, that you can see. So the first option is not correct. In the second option, A star A is not a normal matrix. Actually, this is somebody asked as a doubt in the first problem. That means that is A star A is Hermitian matrix. So this is normal matrix trivially. B option, A star A is Hermitian. That implies A star A is normal. But it is in the option, it is given that it is not normal. So that option is also not correct. Third option is, if X is the eigenvector of A, then X transpose is equal to identity matrix of order n cross n. So this we have to check. Can anybody say if A is normal, what are the eigenvalues of A? Does anybody have any idea about this? All eigen vectors of A are orthogonal. Whenever A is normal, we have that all the eigenvalues of A are orthogonal. That means its norm has to be equal to 1, and the inner product with two different eigenvectors has to be equal to 0. That means it is given that let x be an eigenvector of A. So then we have that, suppose let me write x equal to the some values a1, a2 and so on, an whole transpose. This is the eigenvector of A. Then we have that it is orthogonal. That means x into x transpose, x into x transpose, or x transpose into x. It is asked x into x transpose equal to identity. But firstly let me state the property of this x transpose into x. This is nothing but we'll get a1 square plus a2 square plus and so on an square. This is equal to 1. This is nothing but the definition of orthogonal matrix. But in the question, in the option, it is asked that x into x transpose equal to identity or not. This we have to check. Let me write the product x into x transpose. What it is? X into x transpose. Suppose this is equal to identity. Then we will see what is happening. So we have x into x transpose is nothing but x into x transpose equal to a1, a2 and so on an, and this is x transpose is a1, a2 and so on an. So we will get this matrix is equal to a1 square, a1, a2 and so on a1 an, a2 a1, a2 square and so on a2 an and so on an, a1, an, a2 and so on an square. Suppose we have supposed that this is equal to identity matrix. This is nothing but 1 0 0 and so on zeros, 0 1 and so on zeros, 0 0 and so on 1. So by comparing the elements we get that a1 square, actually ai square equal to 1 for all I, comma ai aj equal to 0 for all I not equal to 0 j. Can we say any contradiction from this? Can anybody expect how? Anybody? We have to say some contradiction from this. Let me reveal. So we have ai aj equal to 0 for all I not equal to j. That implies ai equal to 0 for all I. Can I say this? From this, let me call this one property. This is second. So yes.
Yes, sir. You can say this.
Yes. Because let me from the second we can write a1 a2 equal to 0. That implies either a1 equal to 0 or a2 equal to 0. Suppose a1 equal to 0. From that, by the remaining equations we can say a2 equal to also 0. From that, by repeating that by recursion we can say all elements are zeros, but which is a contradiction to the first equation, that ai square equal to 1. Whenever ai equal to 0 we have ai square is also equal to 0, but we got ai square is equal to 1, so which is a contradiction. So our supposition is wrong, that x transpose cannot be equal to identity. So x transpose not equal to identity. This is about third option, I think. Yes. So the fourth option here, it is A and A star A have same eigenvectors. This is also based on some property of the normal matrix. So the fourth option is A, and of course we remain with this option only. All the remaining three options are wrong. So we can say this option is the correct. But let me prove this how it is. Have same eigenvector, same vector or not. This we have to check. We have a property that when x is an eigenvector of A, let x be an eigenvector of A, that is Ax equal to lambda x. From this, by the definition of normal matrix, we have that A star x is equal to lambda bar x. This is just one what is it say, some result of normal matrix. Whenever x is an eigenvector of A, we have x is eigenvector of A star also, of course corresponding to the conjugate of that eigenvector. By using this, we will see the option how it is. So we have that. Let me proceed with A star Ax. This is equal to A star. We have that Ax equal to lambda x. Because lambda is a scalar, I can write this outside. That means this is equal to lambda times A star x. Again, this is equal to lambda times lambda bar x. So we have that A star Ax equal to lambda bar x. From this we can say x is also eigenvector of A star A. Therefore x is eigenvector of A star A. Of course, the calculation is reverse also. That means it is if and only if. Whenever x is eigenvector of A star and A star A, then we have x is eigenvector of A also. So from this we can say A and A star A have same set of eigenvectors. Is it clear?
Sir, is lambda bar is the eigenvalue of A star A? Na? Is
Yes.
it the eigenvalue of A star A?
Yes. Because A star and A are commuting, so here we have that lambda bar is eigenvalue of A star and lambda is eigenvalue of A. So their product is the eigenvalue of this product also. That happens.
Oh, okay. A product.
Yes.
Okay, sir.
This product is eigenvalue of this product.
And so the
Yes.
first implication Ax is equal to lambda x if and only A star x is equal to lambda bar x.
Yes.
Why?
That is just one property of the normal matrix. For a normal matrix, yes.
We can prove it by taking the star on both the sides.
No, not like that. There is some calculation for this. Here, not by just simply taking star. Some other calculations are there that you can check in some standard book or internet. You can just simply search for the eigenvectors of normal matrix. Then you can get the proof for this. So that is about second problem. So the correct option is D. The third problem here, it is the value of B for which the matrix is positive definite. This is simple. We have a property for a matrix that if it is positive definite, then all the principal minors of that matrix has to be positive only. By using that property, we will check what is the correct option. The third problem, the given matrix is 2 1 b 1 1 0 B04 is positive definite or not? So we will just simply check the the principal minors of this matrix. Principal minors are nothing but just omitting some columns. That means let me explain. We will check three principal minors. That is this one, the first element, and the second one is the determinant of the 2 cross 2 matrix, this one, and the third one is the determinant of this total matrix. We will check those three minors. If those three are positive, then we can say this is positive definite. This is if and only if condition. If A is positive definite, those three values has to be positive, and if these three positive are positive, then we can say A is positive definite. So the first one, principal minors of A are, the first one is 2, that is of course positive.
4.
Yes, the second one is the determinant of the matrix, this one, this is equal to 1, 4, no not 4. So the determinant of the total matrix, that is 2 1b 1 1 0 b 0 4. We will check this has to be positive. For A has to be positive definite, that means this has to be positive. To be greater than 0. So the determinant of this matrix is 2 times 4, that means 8. Let me write it completely. 2 times 1004 minus 1 times 10b4 10b4 plus b times 11b0 b0. This has to be greater than 0. This is 8 minus this is 4 plus b times minus b. This has to be greater than 0. That means 4 has to be greater than b square. That means minus 2 has to be less than b has to be less than 2. So whenever b is in this range, we have this matrix is of positive definite. So let me show you the options. So from this we can say the option B is correct. Is it okay, or anybody have any doubt in this?
No, sir.
Thank you. So the fourth problem, here it is, the matrix associated with the quadratic form. Given some quadratic form. Yes, just it is asking the matrix of this quadratic form. I think you all know, if you are following the classes, you can get to know how to write the matrix corresponding to a linear corresponding to quadratic form. So let me write the matrix quadratic form here. Q of x1 comma x2 comma x3. This is equal to, given it is 8 by 5 x1 square. I'm just writing directly here because I have written on a paper so that I can save the time. You can just check this in the document which after I will share with you. 5 by 2 x2 whole square, 1 by 2 3x2 plus 4x3 whole square. Just expand this by just square, expanding the square. This is x1 square plus 2 by 5. This is x1 square plus 25 by 4 x2 square minus 5 x1 x2 plus half times 9 x2 square plus 16 x3 square plus 2 into 3 6 24 x2 x3. So this is nothing but 8 by 5, or let me write directly. Let me write one more step that makes the calculation simpler. X1 square plus 2 by 5 x1 square plus this is 5 by 2 x2 square minus 2 x1 x2 plus 9 by 2 x2 square plus 8 x3 square plus 12 x2 x3. This is equal to, we have x1 square here and here, so this is 2 x1 square plus x2 square we have here and here, this is 14 by 2, that means 7 x2 square. For x3 square we have only one term, that is 8 x3 square. For x1 x2 we have only minus 2 x1 x2 plus 12 x2 x3. This is what actually given the quadratic form. This is just the simple calculations. From this, can you say what is the matrix? Therefore,
Sir, it is 2 minus 1 0.
Yes, the matrix associated is
2 minus 1 0.
Yes, 2 minus
minus 1 0
minus
minus 1 7 6.
Yes.
608.
Yes. Yeah.
Six,
Let me 608.
Yes, sir. 608.
No, if it is 0 here, then it has to be 0 here only.
068.
Yeah, 068. Yes. Let me explain how it is. So.
Yes, sir. Yes, sir.
Yeah. So, firstly, for the people who don't know how to write this, so firstly we have to check the coefficients of x1 square, x2 square, and x3 square. The coefficients of these values has to be written in the diagonal form. This 2, 7, 8 that you can see, these are nothing but the coefficients of x1 square, x2 square, x3 square. Actually, how it is, this is, let me write x1, x2, x3, x1, x2, x3. So when we multiply this column with this row, we will get the value of this 2 is x1 square. So that is nothing but the coefficient of x1 square in the quadratic form. Here it is the coefficient of x1, x2. We have to write the half of that coefficient. Half of the coefficient of x1, x2. We have that coefficient of x1, x2 is minus 2. Half of this is nothing but minus 1. Why we are writing half is the term x1 x2 will get that in this corresponding matrix 2 times. That here it is, we will get x1 x2, and here also we will get x1 x2. So we are getting this 2 times, so we'll write the half of the coefficient of x1 x2. Similarly, the coefficient of the half of the coefficient x3 x1 here. Similarly, that here it is, the 6 is the half of the coefficient of x2 x3. The half of the coefficient x2 x3 is 12 by 2, that is 6. This is how to write the matrix corresponding to one quadratic form. Is it clear for the people who don't know how to write it, or anybody any have doubt still? If not, I will proceed with next problem. So the correct option is 2 minus 1 0 from the options. I think the third option, C. This is the correct option. Yes. So the fourth option here, it is also simpler, simply like the fourth problem. So the quadratic form here, it is given this, again a 3 cross 3. Which of the following statement is true? Q is positive definite, Q is semi-definite or not positive definite. Yeah, we have to check which is it is positive definite or not. Firstly, let me write the matrix corresponding to this quadratic form. From that, this is nothing but just the combination of the problem third and fourth. Yes, in the third problem it is asked about
Sir.
positive definite? Yes.
Sir, actually, this is exactly similar to the previous question, sir. The last questions are difficult, and there is only 15 minutes time left. Jordan blocks writing that is difficult, sir.
Okay.
Because this question is similar to the previous ones only, we can do, sir.
Yeah. Okay. So this is nothing but just write the matrix corresponding to. Let me write how to do it. Write the matrix and check. So the sixth problem is also simpler. It is if you get the if you write the diagonal form of the matrix or corresponding to this quadratic form, you will get the answer. But okay. So in the seventh problem, it is nothing but the triple pair number of positive eigenvalues, comma number of negative eigenvalues. Sorry, number of negative eigenvalues.
0.
Yes. Number of zero eigenvalues. If you write the numbers in triple pair, you can get the answer. Yes, this is also eighth problem. Do you want me to explain this eighth problem, or can we proceed with the ninth and 10th?
No, please discuss eighth problem.
Okay. So let me explain that. So the minimum of the quadratic form exists at, it is given a quadratic form. I think if you are following the class videos, we can answer this directly. Just write the form in matrix form, the quadratic form in matrix form. So the quadratic form, it is given that is equal to x1 square plus 6 x1 x3 plus 4 x2 square 4 x2 x3 plus x3 square plus 2x1 minus 4x2 minus 3x3 plus 7. This is the quadratic form given. So the matrix corresponding to, actually this is not in the triple pair, that means not as a quadratic form given in the above problems. So of course this is also simpler to write in the matrix form. So the matrix form is, let me explain how to write the matrix form. Q of x1 x2 x3 equal to, for the similar to that problem, we have to write this is equal to 1 x1 x2, we don't have
0,
that,
3,
0, this is
3,
3, this is
0,
0
4, 0,
0 4 0. Okay,
3, 0.
sorry, this is not, this is 2 only, I think. So this is 3
Correct.
3 2 1.
1.
Of course we remain
Minus
with the, yes, we
2
remain,
x.
yes, this is equal to x transpose into x minus 2 times x1 x2 x3 into, we have to write the coefficients of x1 x2 x3, actually the half of the coefficients x1 x2 x3 in this column matrix. This is nothing but 1 minus 2 minus 3 by 2, actually plus or minus here, it is plus.
Minus. First one is also minus.
Where? Here?
Plus. So
Here
minus, sir. I think it's minus.
here it is minus. Yeah, so this is equal to, here then we will get minus,
1,
it is 2, okay, this is
2, 3
3
by
by
2.
2, okay, plus the constant term whatever we have. Treat this matrix as x transpose A x minus 2 times some matrix 2 times x b plus some constant c. Then this is x transpose. So then the minimum value exists at minimum value exist at A inverse B. This is just a straight point that you can see from the class notes if you are following. So from this, just calculate the matrix A inverse B. Then you will get some column matrix 3 cross 1. That is nothing but the correct option from the given options. Is it clear? You just do the calculation for that A inverse B. Of course, for whatever the value C here it does not matter. It does not, the minimum value exists at the same point. Is it clear?
Yes, sir.
Okay. So the ninth problem, here it is. Let A be a 6 cross 6 matrix with minimal polynomial. It is given some polynomial and the matrix A minus I has rank 4. Then the total number of Jordan blocks in the JCF corresponding to A. So the minimal polynomial here it is of order 4, degree 4, sorry, that you can see, and it is given one more condition that the matrix A minus I has rank 4. From these two properties we have to check. Okay, we'll do this. The ninth problem, you do this for the eighth problem. So minimal polynomial MA of x, it is given that x square plus 4 into x square minus 1. It is of degree 4 that you can check, and one more condition given that the rank of A minus I is equal to, what it is given, 4 I think. Yes, 4. So let me write the minimal polynomial as, this is nothing but x minus 2i x plus 2i into x plus 1 x minus 1. Do you agree with this? Is it correct? No, I think the polynomial is,
Yes, sir.
actually that is okay, but the polynomial given it is that x minus 1 whole square.
Okay.
X minus 1 whole square. So we cannot write this x minus 1 whole square. So okay, so let me write the Jordan canonical form JCF. It is 6 cross 6 order. So from the minimal polynomial you can check that the GM, the geometric multiplicity of the eigenvalue 2i is 1. So it can have only the order of the Jordan block corresponding to this eigenvalue 2i is at most 1. That means it can have only one block of order 2i. Let me write it in brackets. This is of order 1 cross 1 because there is only one, this power is 1. Similarly we can write the order of the Jordan block corresponding to the eigenvalue minus 2i is of order 1. This is minus 2i. This is of also order 1 cross 1. This is just from the this minimal polynomial. But if you see that the power of the x minus 1 is 2, that means it have at least one block of order 2 in the JCF form. That means the next one here it is, the eigenvalue is 1. That means it can have of order 2. The block of order, sorry, the what is it? The order of the Jordan block corresponding to the eigenvalue 1 is at least 2. Actually not at least, it is equal to 2. It have at least one block of order 2. This is 2 cross 2. So with this we covered 4 eigenvalues. Again we remain with the 2 eigenvalues. These 2 eigenvalues we can write here, we can write 1 1 also, or minus 2i plus 2i also, but that we don't know how what to write. But it is given that one more condition, that rank of A minus I equal to 4. From this we can check what is the other values in this Jordan block. So we have that rank of A minus I equal to 4. From that we can say geometric multiplicity of 1 is equal to 6 minus rank of A minus I. This is nothing but 2. This is nothing but the geometric multiplicity of 1 is nothing but the number of Jordan blocks corresponding to this eigenvalue 1 are equal to 2. That is the number of.
Sir, is this a property, sir? Geometric multiplicity of 1 is equal to 6 minus rank of A minus I.
Yes, yes. This is one. This is a simple formula. Actually, this comes from that when you solve the equations making Ax equal to lambda x. This comes from there only.
Okay.
Then that is the number of Jordan blocks. Corresponding to eigenvalue 1 or 2. That means the another block also is of order 1 2 cross 2, and that has to be this only. Here it has to be 0. For the eigenvalues 2i and minus 2i also you can check that. We have that geometric multiplicity has to be less than or equal to am, and am of 2i is gm of 2i has to be less than or equal to am of 2i. This is equal to 1. From that we can say geometric multiplicity of 2i equal to 1. That means the Jordan block corresponding to the eigenvalue 2i is of order 1 cross 1. Similarly for minus 2i also. But we have for the eigenvalue 1, it is given by the condition rank of A minus I equal to 4. We can write there should be 2 blocks. These 2 blocks of order 2 cross 2. Is it clear? Of course, the remaining elements all are zeros.
Okay, sir. Understood. Thank you.
The other people, is it clear?
Yes, sir.
Okay. If you have any doubt, you can ask
But
me
sir,
now only. Yeah.
but sir, why we can say that the geometric multiplicity or GM is equal to the number of Jordan blocks? Means what is the logic behind it? I know this is a property.
Yeah. Let me explain. So from this, do you agree that two similar matrices have same properties? I mean, same geometric multiplicity of each eigenvalue, and of course trace, this determinant, all those properties.
Yes,
Do you
sir.
agree?
Eigenvalues are same for the
Yes.
single.
Yes. So if you check that rank of this matrix, suppose this is equal to some m. If you check m minus I, the rank of this matrix also has to be equal to 4, because
Yes.
the matrix given A is similar to this matrix JC M.
Yes,
So from if you check that the rank of m minus I has to be equal to 4. Suppose if you write 0 here, then you will get the rank of this rank of m minus I equal to 3 only. But that is not equal to the rank of a minus I, because two similar matrices have that same properties. By that property we can write this. This is just nothing but the property two similar matrices have similar properties. That properties contains trace, determinant, the rank of the matrices A minus that lambda I corresponding to each eigenvalue lambda. That you can check if you do. Okay, let me explain because I started. So if you do that m minus I, suppose this is equal to m. If you do m minus I, you will get, here it is minus 1, here it is minus 1. You will get this is equal to 0, this is 0. These two elements are also zeros. So the number of non-zero rows are, this is one row, this is one row, this is one row, this is 0 row, not this one. So this is another row, that you can check. So 4 rows. So the rank of the matrix M minus I is 4. This is how it is. So the number of blocks are here 4. So the correct option is C. So the 10th problem here it is the Jordan canonical form of the matrix A. Of course this is also simple, but for this you have to calculate the eigenvalues here. But let me explain the simple way here. As I told you just 1 minute back, similar matrices have same properties. That means trace has to be same, determinant, of course the rank of that corresponding rank of A minus lambda I corresponding to each eigenvalue. This has to be same for two similar matrices. If you check the rank of the the trace of the given matrix A here, that is trace of A equal to what is it, 5. So just check among the options which one have the same trace. So from that we can remove these two options. So among the first option and second option, one has to be correct. But it is given that the only difference here it is of order 2 cross 2. Sorry, it is in the first matrix, in the first option, the number of Jordan blocks are 3. That means the geometric multiplicity, I am explaining about first option. This is about first option. Geometric multiplicity of 3 equal to 2. Yes, 2. If you check that determinant of the rank of A minus 3i, this is also equal to 2, then we can say the first option is the Jordan canonical form of the given matrix A. Suppose it is not, the rank of the matrix A minus 3i is not equal to 2, then we can say the first option is not correct. In the second option, we can check that geometric multiplicity. Oh, what I wrote? It is 1, I think. It has to be 1 here. For the second option,
Yes,
geometric
2.
multiplicity of 3 is
3 is
2.
2. Correct.
Yes. You just check the A minus rank of the matrix A minus 3i. That is either 1 or 2. That has to be.
Okay.
From that properties, we can say among the first two options, we can say what is the JCF. Of course, the first you have to check for the eigenvalue minus 1 also. But here we have the geometric multiplicity of 1 equal to algebraic multiplicity, that is also equal to 1. We don't need to check for that eigenvalue. It is just enough to check for the eigenvalue 3.
But sir, in option 1, the GM of 3 is equal to 2, I think, because the number of Jordan blocks of lambda is equal to 3 are 2 of order 1 cross 1 each.
No.
So why we write GM of lambda is equal to 3 is 1?
Yeah, as I wrote, this is GM of.
Because it's 1 plus 1, sir.
Yeah, let me tell you. The geometric multiplicity is nothing but the order of the matrix, that is nothing but 3 minus rank of A minus 3i. Is it correct? I think then it has to be 2. Here it has to be 2. It has to be 1 here. Yeah. What is your doubt?
So my doubt is the GM tells for an arbitrary lambda eigenvalue.
Yes.
GM tells us the number of Jordan blocks.
Yes.
And in option,
not the number of Jordan blocks, the degree of the highest Jordan block. Sorry, order of the highest Jordan block. Here in the second option,
okay.
Yes, it is of order 2 cross 2. Here it is of order 1 only for each. So the highest order is in the second option it is 2. In the first option it is 1. Not the number of Jordan blocks. It tells the order of the order of the Jordan block. Yes. you just check the values of this the rank of the matrix A minus 3i. From that you can get.
Sir,
Do
one
that.
question, sir.
Yes.
That first matrix you show me, sir, the first option.
Yes.
First
Yes.
option.
Yes.
So here, number of Jordan blocks are 3, no, sir?
Yes.
In the second one, it is 2.
Yes.
Okay, sir. So
Yes.
geometric multiplicity here is 2, and in the first one, it is 1.
Yes.
Okay.
Even if
Thank
you see in the first option, the Jordan block is in diagonal form. That means all the diagonal entries are non-zeros.
Eigenvalue.
Yes, all the eigenvalues are non-zeros and the rest are zeros. So from
Okay.
this you can say if this first option is correct, then we can
Okay.
say A is diagonalizable. That you can say by that minimal property also, minimal polynomial.
Yes, it is diagonalizable. So we need not have to use this canonical form, right?
Yes.
You can do diagonalization.
Yes. If suppose this first option is the correct, then A has to be diagonalizable.
Diagonalizable. Then
Yes.
I don't have to do that. This one splitting factorization.
Yes, you don't need to do. You just
Okay.
simply check the minimal polynomial. Whatever,
Yeah, yeah.
and there are many ways
So
you can check.
if because it is diagonalizable, arithmetic multiplicity, algebraic multiplicity, and geometric multiplicity will be same.
Yes, has to be same.
Okay. Okay. Thank you.
Yes.
Okay, sir. Thank you.
Yeah. Okay. Other people, anyhow, any doubt?
Yes, sir. I have.
Yes. Actually, here I have one more doubt. I'm not sure about these two. The geometric multiplicity of 3 is equal to 1. Yes. This is, we'll get this is equal to 3 minus rank of A minus 3i. A minus 3i. This is equal to 2 actually. Here it has to be 2 and it has to be 1. Here it has to be 1 and it has to be 2. Yeah, sorry, I told the degree, that is not correct. The number of Jordan blocks.
Yes.
Yes, somebody was saying that argument. Geometric multiplicity is the number of Jordan.
Number of Jordan.
Yes, number of Jordan blocks, not the degree. Yes.
Okay.
Yes.
So, sir, my doubt is I'm confusing about this statement. For a real symmetric matrix,
Yes.
the eigenvectors corresponding to distinct eigenvalues are orthogonal.
Yes.
But if the eigenvalues are same, then this result is also true.
If the eigenvalues are same.
Same. For a real symmetric matrix, then we can also say that the eigenvector corresponding to the same eigenvalues are same or orthogonal.
No, need not be.
Need not be.
Yes,
But
need not
sir,
be.
there is a one statement, spectral. I think spectral theory,
Spectrum theory. Yes.
spectral theorem for
Yes.
symmetric matrix. It says that for any real symmetric matrix, eigenvectors are orthogonal. But I am for identity. Let's say we have identity matrix and all the eigenvalues are 1, 1, 1.
Same. Yes.
Then and eigenvectors are also same.
Yes.
And in the previous assignment,
Yes.
there is also for kind of question this is
Okay.
for a real symmetric matrix, there are 3 by 3. There is a 1 3 by 3 matrix, and means we have to find a constant which is in the eigenvectors. We have to find the value of constant
Okay.
which is in the eigenvectors, and
Okay.
we have to use the property that the eigenvectors corresponding to distinct eigenvalues are orthogonal.
Okay.
So and in that option, in that 3 by 3 matrix, I think eigenvalues are same, and means some are same and some are distinct.
Okay.
So I'm confusing about this statement.
You just take the eigenvalues for corresponding to distinct eigenvalues and do that inner product. From that we can get, I think.
Yes, sir. I'm pretty sure that eigenvectors corresponding to distinct eigenvalue. We have to prove means this there is a proof for distinct eigenvectors. Sorry,
Okay,
distinct eigenvalue orthogonal. But
that
for the same eigenvalue,
value is those are orthogonal or not? That is your
yes,
doubt.
yes,
Okay, I am also not sure about this. I think that need not be orthogonal. I'll check that and I'll tell you in the next class. I'm
okay,
not sure, but I think need not be orthogonal.
yes,
Okay, I'll check and tell you in the next class.
Sir, this write up, no, this you please upload it, sir. You have last time also you had uploaded. Thank you.
Yes. Okay, I'll upload.
This, yeah.
Okay.
Okay, sir.
And sir,
Thank you, sir.
this assignment and solution you are putting where are solution? Where means you have to upload this.
You are not getting that links. I think when you log in to this course in that swayam.government.
Yes, yes,
Yeah,
yes.
in the there is in the left side corner in the last in the down there is one I think problem solving session.
Okay,
If you click on that, there is one link. If you open that link, you can get the link for this class notes and for YouTube videos also.
okay. Thank you.
Okay.
Sir, once discuss of number 5 and number 6 bits, sir.
In this assignment,
Yes, sir.
okay. What is the time? Okay, time is over, but okay. Okay, let me explain here only. So for this, the matrix corresponding to this quadratic form is this is 8 x1 x2. So we'll get this equal to 2. This is 2. This is again 2. X2 square, that is coefficient of x2 square is 3. This is x2 x3. This is minus 2. This is 2 minus 2. This is 4. This is the matrix corresponding to the quadratic form. So we have to check the principal minors here only. So that the principal minors are the first one, that is 8 greater than 0. So let's go to the second order principal minor, that is 8, the determinant of the 2 cross 2 matrix, 8 2 2 3. This is nothing but the first 4 elements this matrix that we have to take. Of course this is also greater than 0, that you can check the total determinant of this matrix, and determinant equal to this is 8 times 12 minus 4. 12 minus 4, this is 8 minus 2 times 8 plus 4, this is again 12 plus 2 times minus 4 minus 6, this is minus 10. Minus 4 minus 6 minus 10 minus 2 12 8 8 plus 4 12. Okay, this is equal to 64 minus 24 minus 20. This is equal to what is this 20. So greater than 0. So all the principal minors are greater than 0. That means all the principal minors are positive. So from this we can say it is of positive definite. Is it clear?
Yes, sir. Sir, indefinite means what is the condition, sir?
Indefinite means it is not either positive definite or not negative definite. That means if you get that means x transpose ax equal to is greater than 0 for some vector x and less than 0 for some another vector x. This is just simply not neither positive definite nor negative definite. Is it okay? Suppose each this all the principal minors are negative, then we can say it is of negative definite. Suppose if it is positive for some values, I mean if suppose for some principal minors it is positive and some principal minors it is negative, then we can say it is indefinite. Is it clear? Is it clear?
Yes, sir.
Okay.
Yes, sir.
So for the sixth problem, simply just write the matrix corresponding to this. This is nothing but 9, 3, 3, 9. So it is asked the equivalent diagonal form of this quadratic form. Actually, this is the quadratic, the matrix corresponding to the quadratic form. So the diagonal form of this matrix is, actually this is symmetric matrix, so it is diagonalizable. The diagonal form is nothing but the eigenvalues. This has to be 0 and this has to be 0. And the diagonal entries are the eigenvalues of this matrix. Can you say what are the eigenvalues of this matrix? I can directly say 12 and 6 are the eigenvalues. Can you guess how? From this matrix, can you identify this trace equal to 18 and determinant equal to 81 minus 9, 72? Can you identify this?
Yes, sir.
So it is of 2 cross 2 matrix. So AB has to be equal to 72 and A plus B has to be equal to 18. If you solve these two equations, you will get A equal to 12 and B equal to 6. That is just simple. You can check that. So I can write this is the diagonal form. So from this we can say the diagonal quadratic form is which one? The first option. Is it clear? It is just asked the diagonal form. First you write the diagonal matrix of this corresponding quadratic form and just multiply with this by that x transpose and x. You will get that quadratic form.